We are studying the second chapter, Calculus of Scalar Fields. In the earlier module, we defined vector derivatives. In this module, we shall also study properties of vector derivatives. We start by stating the learning objectives for this module. After studying this module, we shall be able to know properties of vector derivatives of a scalar field. We pose a question: if at a point of a scalar field, if all the vector derivatives exist, can we say that the function is differentiable at the point? We shall try to find an answer to this question in this module. Finally, we shall state mean value theorem for vector derivative of a scalar field. First of all, let us recall the definition of vector derivative of a scalar field. Let A be a subset of Rn, A is an interior point of the set A, and F is a scalar field defined on the set A. As A is an interior point of the set A, we can always find an open sphere SAR which lies entirely within the set A. The vector derivative of f with respect to the vector y at the point A is usually denoted by the symbols dyfa or f dash ay and is defined by limit of f plus hy f of a plus hy minus fa by h as h approaches 0, provided the limit exists. We have also seen in our earlier module that we can also include the case y equal to theta, and in the case for every interior point of the set A, f dash a theta exists and equals 0. In fact, we have already seen for any real number c, f dash a cy equals with c f dash a y provided they exist, that is d cy f a equal to c times dy f a. If we consider that notation f dash a y, then we can find that f dash is homogeneous with respect to its second entry. Now, we start the other properties of vector derivatives of a scalar field. Let f and g be two scalar fields defined in some neighborhood of a point A in Rn such that for some y in Rn, both f dash a y and g dash a y finitely exist. Then f plus g dash a y exists, and moreover f plus g dash a y equals with f dash a y plus g dash a y, that is dy f plus g a equals with dy f a plus dy g a. Now, we give a proof. Let us define h equal to f plus g using pointwise principle. So, the domain of the new function h will be the intersection of domains of f and g. So, h is defined in some neighborhood of the point A, and we find h dash a y. By definition, it is limit of h of a plus t y minus h a by t as t approaches 0, provided the limit exists. Now, we replace h by f plus g, then we find the quantity is f of a plus t y minus f a plus g of a plus t y minus g a by t. Now, both the limits, limit of a plus t y minus f a by t as well as g of a plus t y minus g a by t exist as t approaches 0. So, we have f plus g dash a y equals with f dash a y plus g dash a y. Another property. Let f be a scalar field defined in some neighborhood of a point A in Rn such that for some y in Rn, f dash a y finitely exists. We shall prove that for every real number alpha, alpha f dash a y exists finitely in that neighborhood of A, and alpha f dash a y equals with alpha f dash a y. Now, since A is an interior point of the domain of definition of the scalar field f, we can always find an open sphere SAR in which the scalar field H equal to alpha f is well defined. The value of R will depend on the value of alpha. Here also we defined H by pointwise principle. We observe H dash a y equals limit of h of a plus t y minus h a by t as t approaches 0 provided the limit exists. We replace h by alpha f and then apply the definition of alpha f. So, that is we have alpha times limit of f of a plus t y minus f a by t as t approaches 0, and that is nothing but alpha f dash a y. So, alpha f dash a y equals with alpha times f dash a y. Now, an observation. Let A be a subset of Rn, f is a scalar field defined on A, and A is an interior point of the set A. Also, let y be any non-zero vector in Rn such that f dash a y exists. Then for any non-zero t, we can write f of a plus t y minus f a equal to product of t with the ratio f of a plus t y minus f a by t. We take the limit of both the sides of the above expression as t approaches 0. In the right hand side, we have product of two quantities, and for both of them the limit exists as t tends to 0. So, we have limit of f of a plus t y minus f a as t approaches 0 equals with f dash a y multiplied by 0, and hence it is 0. This shows that if f dash a y exists, then f is continuous at the point A, but only along the line passing through the point A and parallel to y. We have already seen that if f is a scalar field defined on some subset of Rn such that A is an interior point of domain of f and f dash a y exists, then for every real number c, f dash a c y exists and it equals with c times f dash a y. In other words, f dash is homogeneous with respect to its second entry. So, natural question is f dash additive with respect to its second entry? Now, we try to find an answer to this question. Let A be a subset of Rn, A is an interior point of the set A and f is a scalar field defined on A. Let u and v are members of Rn, both non-zero, such that f dash a u and f dash a v exist finitely. Now, the question is regarding the existence of the vector f dash a u plus v. We show that it may so happen both f dash a u and f dash a v exist, but not f dash a u plus v. We cite an example. We define a scalar field f from R2 to R as follows: f x y defined by modulus of x if x equals y and otherwise it is 0. We consider the unit coordinate vectors u1 equal to 1 0 and e2 equal to 0 1. We find that d e1 f at the origin, that is nothing but f dash theta e1, that is del f del x at the origin, it is limit of f of theta plus T1 minus f theta by t. So, it happens to be f of T0 minus f 0 by t as t approaches 0, and we find that it is 0. So, del f del x at the origin is 0. Similarly, we can show that del f del y at origin, that is f dash theta E2 is 0. Now, let u equal to E1 plus E2. So, U1 has both components 1. Then f dash theta u equals f of theta plus Tu minus f theta by t as t approaches 0. It happens to be limit of f tt minus f 0 by t as t approaches 0. Now, f tt is nothing but mod t. So, we have f dash theta u if exist the limit of mod t by t as t approaches 0. We know this limit does not exist, as the left hand limit is -1 and right hand limit is 1. So, it contradicts the uniqueness of limit and hence does not exist. This asserts that f dash a u plus b may not even exist whenever both f dash a u and f dash a v exist finitely. From the very beginning, we are searching for a suitable definition for differentiability of a scalar field at an interior point of its domain. Our first attempt was that if at an interior point of a scalar field, if all the partial derivatives exist finitely, can we say that the function is differentiable at the point? We failed, because if it is the definition of differentiability, we found that it does not imply continuity. After partial derivatives, we defined vector derivatives. So, we now make a new attempt. Our new question is, if for a scalar field at an interior point of its domain, if all the vector derivatives exist, by existence of all the vector derivatives we mean for each vector from that space, then can we claim the scalar field is differentiable at that point? We are now trying to find an answer to this question. So, we now ask the question, let f be a scalar field defined on the set A, where A is an open set in Rn and A is a point in the set A. Since A is an open set, obviously the point A is an interior point. If for all V in Rn f dash a v exists finitely, can we claim that f is differentiable at that point A? In such a case, we can say that f x tends to f a as x approaches A along the straight line passing through the point A and parallel to V. This we have already proved. Moreover, this is true for every V in Rn. But we are still in dark what will happen if we approach the point A along any curve which is not linear. Let us consider the following example. We define a scalar field f on R2 by the following: f x y equals with x square y divided by x to the power 4 plus y square if x y is different from 0 0 and at the origin the value of f is 0. We select any vector v in R2 arbitrarily. Let the components of Vv, V1 and V2. If V is non-zero, then we have f of theta plus hv minus f theta, that is f of hv1 hv2 minus f0 0. So, that is h cube V1 square V2 divided by h square into h square V1 to the power 4 plus V2 square. We divide both the sides by h. So, we have the ratio f of theta plus hv minus f theta by h equals with v1 square v2 by h square v1 to the power 4 plus v square. This is properly defined only for non-zero values of h. Now we consider the limit as h approaches 0. We find f dash theta v equal to v1 square by v2 if v2 is non-zero, and if v2 is 0 then it is 0. So we find that for every v in R2 f dash theta v exists finitely. Now let us recall the definition of f. It is fxy defined by x square y by x4 plus y square for non-zero xy, and at origin it is 0. Let us approach the origin along the curve, say y equal to mx square, where m is real. We can find out that it gives different values for different values of m. So definitely the function f is not continuous at the origin. Thus we cited an example in which all the vector derivatives exist at origin, but the function is not continuous at the origin. So we conclude that the existence of all possible vector derivatives at a point does not give a satisfactory definition for differentiability. Now we are going to study mean value theorem for scalar fields. All of us are familiar with the Lagrange's mean value theorem of differential calculus for a real valued function of a single real variable. Let us recall it. If a function f is defined and continuous in a closed interval a to a plus h, differentiable in the corresponding open interval a to a plus h, then there exists at least one theta in the open interval 0 1 such that f of a plus h minus f a equals with h times f dash a plus theta h. Now we can show that a similar result can be obtained regarding vector derivative of scalar fields. Mean value theorem for a scalar field. First we give the statement. Let f be a scalar field defined on a set A, where A is a subset of Rn and A is an interior point of the set A. Also let V is a vector in Rn such that for all t from the closed interval 0 to 1, the point a plus tv also lies within the set A. We further assume that for all real t from the closed interval 0 to 1, the vector derivatives f dash a plus tv v exist. Then there exists at least one theta in the open interval 0 1 such that we can express f of a plus v minus f a equal to f dash a plus theta v v. That is, the ordinary derivative in the result of single variable calculus is replaced here by a vector derivative. We give a proof, and in this proof we shall use our known results from single variable calculus. We define a function g whose domain is the bounded closed interval 0 to 1 and g is real valued. We define g by gt equal to f of a plus tv for every t from the closed interval 0 1. By proposition, g is well defined, and moreover it is differentiable on the closed interval 0 1. Hence, it is also continuous on 0 1. So, we are eligible enough to apply Lagrange's mean value theorem for the function g over the interval 0 to 1. By Lagrange's mean value theorem, we can assert the existence of at least one theta from the interval 0 1 such that g1 minus g0 equals with 1 minus 0 times g dash 0 plus theta into 1, which is nothing but g dash theta. That is, we replace g by corresponding values of f. We find f of a plus v minus f a equals with f dash a plus theta v v. This completes the proof. We shall see that the above result is useful to study properties of scalar fields, but only along a line segment. If one wants to deduce the corresponding result of single variable calculus from this expression, let me advise him to start with putting v equal to 1. Please recall that singleton 1 is the standard basis of the linear space R over R. We cite two examples. These two examples show us that mean value theorem for scalar fields are helpful to study some properties of those scalar fields. The first example, let f be a scalar field defined on a set A which is a subset of Rn. We assume that there exists an open sphere SAR which lies entirely within A such that for every point in SAR and every vector in Rn, f dash x y, where x comes from SAR and y comes from Rn, exists finitely and equals 0. That is, at every interior point of the open sphere SAR, for each vector in Rn, the vector derivative exists but vanishes identically. We know that any open sphere is an convex set. We choose any z from SAR arbitrarily, then we can express z equal to a plus y. Now, using mean value theorem, we can claim that there exists theta from the open interval 0 1 such that f of a plus y minus f a equals f dash a plus theta y y. By the proposition, the right hand side is 0 and the left hand side is nothing but f z minus f a. So, what we have f z equal to f a. We recall that z was arbitrary member from the open sphere SAR. Hence, it follows that for every vector z in SAR, f z equal to f a. That is, at every point within the open sphere SAR, the value of f equals to the value which f assumes at the center. In other words, f is constant in SAR. In this example, we can replace SAR by any convex set and we shall get the same result. That is, if at any point in a convex set corresponding to each vector, the vector derivative exists and equals 0, then within that convex set, the scalar field is constant. Another example, let f be a scalar field defined on a set A where A is a subset of Rn. We assume that for a fixed non-zero vector y in Rn, f dash x y equals 0 for every x from the interior of the set A. That is, at every interior point of the domain of the scalar field f and for every non-zero vector y, the vector derivative f dash x y vanishes identically. Now, let A be an interior point of the set A. By definition of interior point, we can always find a positive real number R depending on A such that the open sphere SAR with center A and radius R lies entirely within the set A. Let z equal to a plus t y be any point in the open sphere SAR. Then z minus a equals with Ty, that is the vector z minus a is parallel to y. That is, z is a member of the set LAY, that is the line passing through the point A and parallel to y. Now, we apply mean value theorem for scalar fields here. It asserts the existence of a theta from the open interval 0 1 such that we can express f of a plus Ty minus f a equal to the vector derivative f dash a plus theta Ty y. By proposition, the right hand side is 0, that is f z minus f a is 0, that is f z equal to f a. Now, z was arbitrarily selected from SAR. So, f is constant along the line passing through the point A and parallel to y. Since the point A was arbitrarily chosen, we find that f is constant along every line segment lying in A. But if we select some different line segment, it will be constant also thereon, but with maybe some different value. In this module, we studied some properties of vector derivative of a scalar field. We also studied mean value theorem for this. We cited two examples in which we find that we can use the mean value theorem to study some properties of this function. We have also seen if at an interior point of the domain of a scalar field all the vector derivative exist, it may not imply continuity at that point. So, the existence of all possible vector derivatives at an interior point of the domain of a scalar field does not give us a satisfactory definition for differentiability.